Hello, everyone, and welcome to podcast 44 of the MotorDoc podcast. We got so many people watching, so figure it's good enough to continue. As promised a few weeks back, we are going to talk about bearings. We're also going to do a quick discussion related to CIGRE and some of the things that happened this last week. Including some proposals that we're waiting on the vote to move forward that I'll be participating in. I'll be chairing. And then as the USA rep for CIGRE for A1, which is electric machines. In any case, in addition to that, we're also going to introduce the product we are going to show at the SMRP conference this year, and I'll do an introduction to the beta of the download capability of the system. But this, which is, this is 1 CT. You can use any millivolt per amp CT, but this system here, which utilizes a couple of components that are out there. The main thing will be the software. This is going to be a single-phase straight current signature analyzer that will upload data, allow a quick report from that, but then with features that will allow you to do a full analysis, meaning a lot of the algorithms that MotorDoc has developed will be built into a software for automatic analysis of the electric machine, electrical and mechanical condition, and driven equipment. It's not going to be as nice and easy and all-encompassing as the empath system. As a matter of fact, the idea here is a simple, easy, quick system that'll work on everything from a fractional horsepower to as large as you want, primarily induction motors. We'll add more features as the years wear on. We're going to release the version 0.9, which is still beta, at SMRP in October. And that will be very cost effective. I'm working out the pricing based upon what the team comes up with, but let's just say it will be in the 5-digit range US instead of what we're seeing is a lot of systems moving up in price. The empath system will not increase in price. It's going to remain the same or a little bit less as time moves on, primarily the same, just because of its strong capabilities. And to this day, as discussed during CIGRE as well as at ACP, it's still the only one able to do wind turbines, to the point where a majority of the OEMs and a growing number, all of the US, but a growing number of overseas as well as North and South American companies are utilizing it for that area. We are working on a lot of things to make that electrical signature analysis affordable and available to people, making it both easy, but then also making sure that your experts are able to go in and utilize whatever data is developed. To go along with what we do is our types of systems. We don't charge for support. We don't charge for most upgrades. There will be features that you can purchase separately, but the base system will be upload. The next system, the one that will be available there as well, the upload's done. The other one will be the automated analysis through for induction motors. So with that, that'll be the last part. We'll show you a quick demo of the upload. We still have to, as a beta, we still have to make it look pretty, but it works. So here we have our discussion about bearings and vibration. And I don't know what's happened the past few years, but I swear with the implementation of IoT and the cost of that type of system coming down, which is great. The people that are applying these things, I'm going to be blunt, and I know I'm going to make more friends. They're a mess. It's an absolute mess. We're watching all the mistakes of 40 and 50 years ago happening again. And I get that we have people leaving the industry and everything else. I'm going to blame it on the universities for one. Academia is doing a really, you know what? This one is going to be R-rated. Academia is doing a shit job on training people. I've interviewed people, I've talked to people, they got out of college. All of their experience is simulation and everything else, right? So they come out and they go, oh, vibration, let's stick it in the middle of a machine, things like that. I talked about this a few weeks back, and I showed some stuff that was really disturbing. I'm going to show a couple of those images again and go through what happened and why. And that's the purpose today. You have to understand what you're dealing with. And I'm sorry, theory or some person coming off the street going, oh yeah, I know how to do it. It's one of the reasons why in a lot of industries, let alone wind, people aren't paying attention anymore to their vibration data. They were warned, da-da-da-da-da. Well, when you're warned about something imminently failing and it doesn't, that's one thing. But then on the other side, what we're seeing is people go, oh, look, we caught this. And I see it on LinkedIn all the time. And it's a catastrophic bearing failure that they're showing. We just caught this. I'm sorry. If I see false Brunelling, I'll be calling it a long time before the point where we're talking about. As a matter of fact, I didn't include those images, but we had a 63, it was a 6330 bearing from a wind turbine drive end where vibration had picked up something else, but they focused in on the condition. They said, you know what? We're not quite clear on it because we're seeing a bearing issue with the ESA, and it had just been installed. If they'd run it for too long, it would have failed. The balls were dragging. We're already about to start we hadn't got to the point where they're disintegrating, but they were no longer nice and shiny. And the false Brunelling on the inner and outer race were visible. Vibration barely caught it. They actually caught the high-speed bearing in the gearbox, and it was misdiagnosed, luckily, as the generator bearing. The whole problem had to do with incorrectly placed spacers and a coupling. So we were sent the bearing to analyze, and I take a look at it, and I'm going, wow. And then I take a look at the data I was sent, and I went, yeah, okay, we're seeing 11 kilowatts from the high-speed thrust bearing because of this other thing, but we're seeing another several kilowatts worth of losses from the drive end bearing from these components, in particular the balls dragging. So luckily it hadn't failed at that point. But we're seeing that all the time. And it's a very common reason. It has to do with placement of the sensors. It's not the technology, it's the people. We've had other instances where we've gone in and we've discovered that the settings were wrong and things like that. Again, a people issue, not a technology issue. And then we've had another one recently where, some indicators were showing on a condition and they were like, okay, we need to shut down and take this equipment out. We're shutting down a major site, we'll just put it that way, costing millions per day in lost revenue, because it would literally shut down the ability of this site to do what it needs to do. And when I took a look at the data, I said, yeah, there's something showing up in there. And they cited that it was the bearing because they saw the pulses. And I said, no, it's that the gear is just slightly misaligned, and you're actually seeing the gear rolling we identified the different signatures and said, okay, the bearing has an issue. It has to do with that. But this is something that can be dealt with. How soon do you have a spare available? And they have to have it overhauled. And I said, so you don't need to shut down your plant for a month and wait. Get everything in place, and you're going to have time. Increase the frequency of testing. So let's get into this. And the focus today will be babbitt bearings, although I'll show some ball bearing stuff. I'll start with the ball bearing. I'll start with the babbitt bearing, and then I'll go into the involvement with ball bearing. And the very, very most common issue I'm seeing because of idiots placing the accelerometers randomly on the frame of the machine. I don't know why. It's not the way we were taught from the beginning. And I've been a vibration analyst since I was in the Navy in the mid-1980s. And we were taught, get the darn thing, R-rated. Get the freaking thing right over the bearing housing. Get it so, and the area of the bearing housing where the bearing's in contact. The minute you have space, the minute you have a frame around it where there's no direct contact, okay, so if I have an accelerometer like this, it wants to see the data come right up through it. I know there's triacs, that's structural. But for a bearing, I want to read straight up through it. So I set it down on that housing, and if I have direct connection, I can read it. There'll be some dampening based on the type of material, but it's not going to be a lot. But the minute I have an air gap under there, the minute I have a structure under there where there's a gap, I am not reading directly up through that accelerometer anymore. I'm reading directionally, so it's a vector. It's no longer coming straight up through my accelerometer. It's coming at different angles. As a direct result, I've got dampened readings, meaning they're not effective. Plus, that loose structure creates a resonance, meaning a bell effect. If you ring a bell, it starts ringing at different frequencies based upon the structure. So if I go in, that's the different tones you hear. So if I ding on one, it makes one tone. That's because of its natural frequency. I ding on another and it makes a different tone. That has to do with its natural frequency. So let's take a look as we go through this. And I always like to remind people when we're talking about electrical stuff, especially I'm going to show you that one item at the end. Making something more affordable means people that are less experienced may be handling the stuff. So danger, do not touch. Whenever I'm dealing with electricity, I remember this all the time. It's not fun. I've had my share of zings and zangs and shocks since the 1984 when I went into the military. Being first a Navy electrician and then an industrial electrician and a motor repair guy. Things happen, and they will. And, the whole idea is safety. Make sure whatever you do, wear your cotton glove or plastic gloves when you're handling electricity. I don't know where that's happened, but I'm in the field and I'm watching, people that are, their safety gear is something they got from the hardware store and not actual electrically related gloves. Whole other issue. So let's talk about the purpose of a babbitt style bearing. And this is really, really important. I stole this from a random site online. So whoever made it, thank you. I'd give you credit, but I have no idea. It looked like it was shared from somebody sharing something. Normally don't do this, but this is a really nice image. So whoever did this, kudos. So if I take a look at a shaft sitting in the housing, now in a babbitt housing or journal bearing or babbitt bearing, whichever you want to call it, I will have a gap around the top end of the bearing. It is an air gap, okay? And this is the pictures I'm going to show you. People will put the accelerometer on top. What are they reading? They aren't reading the shaft. So whenever you use a journal style bearing, normally there'll be a spot where you will have a Hall effect or non-contact, or even some will have contact style devices that are reading primarily displacement, lower frequency stuff. But in there, any other reading I take just on, if I were going straight off the journal bearing alone, I'm still only going to be reading indirectly this system. So you notice the load is straight down. I will have oil in there. Now this is a motor with the rotor not turning. And I will have this here. I will have several thousandths of an inch. And if the load's pretty heavy, it'll be the molecular thickness of the oil, okay, down to one molecule thick. And the babbitt, of course, absorbs and holds some of that oil. It's quite porous. Then when it starts, it's going to throw things. So if it's turning in this direction, the rotor is going to try to climb the wall, and it will set up what's called an oil wedge. And then when it gets up to speed, it's going to push to one side, and there'll be an oil wedge developed, and the shaft will shift based upon the oil wedge. So if I have something happening in here and I'm doing an orbit analysis, and I start seeing an orbit occurring, it's because of oil whip or some other condition where the oil is not maintaining that wedge. That wedge is very important for lubrication and to ensure that the shaft does not come into direct contact with the babbitt. Babbitt is a very soft material, and it will peel up really fast. So there's a whole lot we have to worry about when we're creating a babbitt bearing, let alone anything else. It's again a precision surface, and there's a whole lot that goes into lubricating babbitt that's outside the scope of today. Mostly I want to discuss why you have to be careful where you're taking data. This image this is from the IEEE 1068, which is a motor repair standard. This is a typical bearing. It's similar to what's called a rank style bearing, which is a self-centering style bearing. And it's done, and I'll have some better pictures of it, but what I wanted to show is that there's a structure underneath, and the bearing is suspended by two rails that are insulated with an insulating material that is kind of rubberized. It depends on the exact application. There's a couple of different materials that'll be used, but they absorb the energy. I actually remember one case where it had peeled back a little bit, and it was a 1800 RPM synchronous large, about, I want to say 1500 horsepower, 4160, and somebody had gone in there and a piece of that material was missing, and they put in a filler, an epoxy filler, which did not allow any movement, and it caused the bearing to cock and caused the shaft to come in contact with the seal, and that little bit of rubbing caused the rotor to bow, so they constantly had a vibration issue. Anytime the seals come into contact with the shaft, direct contact, it will cause that situation. I was looking for the images for that, wasn't able to find them, but I may cover that as a discussion later. I have a PowerPoint on that entire experience. The oil ring, depending on whether it's pressurized or not, pressurized systems, some don't require oil rings, most will. The oil ring sits on the top of the shaft, and it feeds through the bearing, and it rolls and it pulls oil from the base here up and over on top, so that it gets in between the babbitt and then the top, which is where everybody seems to want to place accelerometers, which is now got all kinds of structure that has no direct bearing, pun pun intended, on the bearing. So typically, it'll look something like this when you see it from the outside. So all the everything for the shaft sits down on the bearing. I've got seals on both ends, lubrication process of some type, an oil return. This is all wide open space, except for mechanical structure to hold it all together and to support the bearing a little bit. But there is no, there's very little direct connection to the base as well. There is far less to the top. So if I'm going to take data on one of these, if I want to take horizontal, I might take horizontal here. I'll take it off the bottom side when I can. And I'll always want to get, if I'm going to use an accelerometer, to get an idea, but not to use the value, I will take from up underneath. I've had ones that will measure 0.06 or 0.09 inches per second on the bottom, yet on the actual non-contact vibration data, we were reading, 0.3, that kind of thing. I mean, it's a significant difference. So if I'm going to take data from there, has nothing to do with the amplitude, has more to do with the pattern of the vibration. So let's take a look. Oh, and this is what I mean. This is the bottom side, another one I shamelessly borrowed. There's the material side I was talking about. So the bearing itself will sit in here, and this can be, as much as I'd say between 1/16 or 1/8 of an inch. So at least for metric folks, several millimeters at a minimum. Thick, and it absorbs. It's flexible. It's soft, right? So the bearing sits on top of that. That's so it can move a little bit. The rest of the structure is just filled with oil, and you can see I have open spaces all over the place. And I've got contact here and here through rubber, and then into a bearing, through oil, and then to the shaft. So there is no way I'm reading an accurate measurement of the shaft through that structure. And if I set my accelerometer right in this area here, well, then I have the natural frequency of everything going on around it. And the fun part is, if I'm going in, depending on the size of the machine and everything else, I'm not quite clear on where I'm coming into contact. In this structure, sometimes these are not in contact with the outside, and you can see that here. That's an example. It's contacting here and here. And this is all the structure that suspends the shaft on this end. So it ends up being connected to the housing. You can see in this spot here, it's bolted there. So the fun part is, and I'll show you some pictures of this, because we did a study to take a look at the value of the data we were getting, and then we were comparing it to the actual vibration from the shaft, so that we could get a baseline, so that when I go in and I do vibration analysis in this particular site, I know the relationship between my vibration data with the accelerometer from specific positions against that data. So because the customer insisted on having, accelerometer data, so I knew how to set my limits based on that. Thinking, right? It's called, physics or something. So let's get into the structure. We'll keep on going that end, because I believe this has got some teardown stuff in it as well. So this is a machine that we had taken apart, and it's actually a 4,500 horsepower 13/8 synchronous machine. Right off the bat, this is a seal. Okay, so you can see the spring around it. This is a variety of materials, but in this case, this is there. It's going to be suspended when everything goes together. It's suspended, and it's got a clearance from the shaft. It's not in direct contact. If we're in direct contact and dragged it all, we create a hot spot, and the whole shaft will move in that direction, the hot spot. Basically, it'll flex or bend. Okay, and then I'll end up with problems. This is the shell of the babbitt bearing. We're working in reverse here. Oil comes in here. This one has a single ring. That ring sits right there, and that's free floating. It just basically turns. Now, in some cases, we've seen it where they become oval or out around or whatever else, and then they end up just sitting on the shaft, and you don't get lubrication, or you don't get much. It won't bring the oil back up and around. This is not a pressurized system. It has oil coming in, but that's about it from the top. And then these are pins that hold the bearing in location, so it doesn't start spinning. It does allow for some rocking of the bearing, because what I showed you before on that gap, this is the part angled on both ends that sits in there. And this is the top half of the bearing, space there for the ring. This is babbitt. So this part here and this part here is the babbitt area. The rest is a steel structure. Okay, now part of what you want to do whenever you're doing this is you need to make sure at least 99%. Well, actually, you can see the difference in color. So that layer, that split right there, that's the babbitt, and the rest is metal, or steel. So we have to make sure that there's strong adhesion, not a lot of bubbles. Not as worried about on this part. Now, this is the type of bearing where you can't flip it over. And you can also see pin locations here again for making sure everything's in place. When it all gets sandwiched together, you're less likely to have anything happen, but you need to have that. I think this is probably just another angle of the same bearing. And I believe this will be a seal. Now, this is seal, and part of the problem we had with this particular application was some increased vibration during operation. You can see this is nice and brownish and shiny, and this is darker, and that's because this rubbed. So that rubbing will cause some of that increased vibration. Very important to know when you have this size machine. Usually show up as a one-time RPM. With electrical signature analysis, it'll show up as a one-time RPM and a dynamic eccentricity, because the rotor is going to orbit, mechanically orbit in the shaft. Here's how the shaft sits. This is what this part is. This is a bearing surface, and I've seen people mark these up. I've seen it in repair shops. These get marked up, damaged. They'll do other things. Most places will take a thick layer of Nomex or some other material. You don't want to use steel because it'll scratch. Nomex is an insulating material, but it provides some cushion, and we'll wrap it around that and then tape it because you need to protect the surface. It is a very, very fine finish. It's got to carry the oil, and you don't want any raised spots, dings, dents, or whatever, because they'll create pressure points that will begin eating away at the babbitt and may cause it to peel up. So you can see the location. The rings go around the outside of the bottom half, and you can see channels for oil. This may be just another angle. Yeah. You can see how fine the finish is. It's not too bad. A couple of scratches here and there, but nothing you can do about that. That's the other end before we split it. And then what it looks like. I'm just showing you everything. That's what the whole shell looks like with that structure underneath. Seals again. Always want to inspect those. Worst thing is to have seals which would go right here, right? if it fails as well, oil will pass right through here, especially if there's a difference in pressure. Matter of fact, the hoses or pipes that come off of the bearing itself include some that vary the pressure inside the bearing so that you don't have oil escape. So if you have high pressure in here and a low pressure in here, you can actually move oil out. This is it's another stopgap for that. The bottom side will be, because your load's going to be straight down. You can see this. This tells me, because I've got nice and shiny over here and narrow shiny as I go in, so kind of this. This tells me that this bearing was not aligned properly. It was actually cocked a little bit, because this should be an even shiny surface across the whole thing. And this is the babbitt. This contact of the babbitt adherence is critical, and one of the tests that should be requested if you re-babbitt a bearing. Re-babbitting is actually relatively common, and usually there's different types of processes. I'm not going to cover that in this one. As you can see, if I were taking a direct reading from here, I'd be closer, but I'm still going to have my oil wedge here, and that could be relatively thick. That's going to absorb some of the vibration from the shaft. And yes, oil is a non-compressible fluid. I've heard that argument, but it's still a fluid, and it's going to absorb some of the energy from the shaft, and then it's being dispersed through a structure. This is the other one. I believe this will be the oil ring. There's an oil ring. Some will have two. Again, you have to be careful that it's not going to get caught or stopped. And it's two halves, by the way. It's not a solid ring. You have to get it on and off. Let's get down to the structure a little bit. And here's the structure. Okay, so this is the bottom structure, and you can see this is Teflon in this case. The other one's rubber. The black is rubber. This is Teflon. This is sitting here, and I have all of this structure in here where the bearing's sitting. And most people take, and I'll show you the location in a minute. This is a more recent one. This is a slightly different bearing, a slightly different system, and final testing had the accelerometer there. Here's one where I took data, and the customer insisted on vibration data. To be perfectly blunt, I didn't care. I was doing ESA and looking directly at the air gap between the rotor and the stator. So just like using the Hall effect type system, but the customer insisted on vibration, so I took vibration. It did give us the ability to add some stuff to a project we were doing. It was also interesting was on this gearbox here, the locations that I found, because there's a bearing right here. It's in a block that sticks out. I was expecting to find an accelerometer position about middle on the opposite side. They had put little magnetic spots that you could screw your accelerometer. No, they put it in the middle of the freaking structure, which is a giant bell. It's hollow. What are you going to get? You can't get any data from that. You can barely imply any data from that. You're doing a structural analysis at that point. You're not actually doing anything with the bearings. You're not going to detect anything early enough. It's ridiculous. It really is. So let's take a look, because this is going to be longer than I expected, apparently. Let's take a look at some data collection. Just real quick. This is an example from, now this is a system that I haven't used in a while. Wireless accelerometer. I'm going off of a magnet base they have in place. We were required to go off of these. Luckily, I had them placed properly. So one was on the side, one was on the bottom. Taking it off the top is completely pointless. Yet that's how I always see people doing it. Again, structural. this is part of the study we did to take a look and see, where we were going to get good data. Yes, that is a metal plate there meant to take vibration. The people that were doing the data analysis from that location previously had set these, and it drove me nuts. So I went ahead and took it, but this is this thick, and there's nothing on the other side. It's big open space. It's not even on the bolt to at least get on the structure. So I'm reading a bell. So dong. Yeah, I'm reading how that structure is vibrating in relation to its whatever. It's just ridiculous. I'm not going to do the videos. This is kind of, I have we have a tachometer feeding into the system and everything else, so we can do phases and vibration just to map out the structure. So this is the setup here, and this is the system here. As you can see, I'm moving it around to different spots just to get an idea. We were mapping out the whole system, and looking at phase angles and a bunch of other things, because we had a base issue in this case. And this was in collaboration with the work. No, this is well before I bought, because I bought the RDI system a little later. So this is how we had to do it before, identifying problems in the system. You notice that I got them down to using proper size shims. In this one, that's another one of my pet peeves. So shims actually go the whole length. Drove everybody nuts, but I'm good for that. If I want it done properly, if I'm going to be responsible for this machine, I want it done right. I don't want any of this half-ass bullshit where they go out and they get these little tiny shim packs and they start shoving them in a machine of this size. So, all over the place, but there's a purpose behind this, right? Am I using this to troubleshoot a bearing or the rotor? Oh, hell no. This is a structural analysis, as I mentioned. So that's the blocks that they had welded on, like that was going to tell me anything. Oh, look, it's a thick piece of metal. No, it's just a different that's going to give me a different tone in vibration. If I were to look at the same vibration in different spots. Now this, am I reading directly the bearing? Oh, no. But I'm reading a lot of things here. So we actually did, one of the projects I did was model this out, because I've been doing machine learning and ESA, with ESA and vibration for a long time. Many decades. We started mapping this out and doing a model to see what happens with the structure and everything else. So while I'm doing the work, we were gathering data for research. This one is, just because of the location, I might say, okay, this is close to an axial, but really, I'm not going to get an axial that's worth anything other than the structure. I might use the shape, but ignore the values and use something else to tell me the severity. Here's a location. So you can see the drain plug right there. So I don't want to be on top of the drain plug, because that's guaranteed to be a hollow spot. So I've tried to move it onto the other side of that so that I can get as close to the structural part as possible to get as good a reading as I can up through the structure, through the bearing, things like that. Doesn't mean that it's going to be good, because again, the bell effect. And then a few more. Let's see if we got something interesting here. No. Now these again, so there's a bearing in this portion here. This is actually a bad spot because the bolt goes through. Really, I should probably take it in the middle there. Preferably, I would take it in a spot where I could get direct, but there's structure there. There was a piece up here for taking data. This is a double row roller bearing, so not too bad, but it's a pretty high speed system. So we took a number of spots, but we had to take them where they'd been previously done. They were all marked. So I did take up there. I took from the side, did something similar on the other side. Yeah, here's, you can see where we took it there. Through paint. Yeah, yell at me. That's absolutely right. That should have been direct to some type of metal. But we weren't given the okay to put anything on the surfaces or to tap. So I'm using a magnet base there. Okay, so that's that bit. Let's take another quick look at... let's take a look at this first, because this was kind of funny. Hey, we're having a vibration issue. We think it's this, that, and the other thing. So we did ESA and discovered there was not actually a vibration issue. We were doing, this is an inrush test, so you can see that there. That's the current. And we're on the low energy side, so this is actually the control cabinet. Still requires, it's not a class 2, it's a class 0, but still required all of the appropriate gear. I'll show you this real quick. So this piece here was in to help them with the alignment, but that piece and that little piece of wood there, which are not in contact in this picture, by the way, go away during operation. And with this big machine here, many tons, they connect it here, and it's landed here, by the way, with a tiny shim pack. What the fuck? So, oh, did that come through? Sorry. I'm speaking Navy today. I get frustrated when I see this stuff, because I'll get called down and, the minute... I don't need to take data. Matter of fact, I think I was the only one who had good data. Everybody else was trying to take data, the OEM, repair facility, everything else. Nobody's data was any good. Our data was good. Both the RDI and the empath data. But this is what I'm talking about. At least they put it under the bolt. Often I'll see this behind it or in front of it, and then when you tighten down on this, you had to start the whole motor. But look how many there are. As a matter of fact, the next picture was supposed to show daylight between those. I don't know if it will, but they aren't even compacted properly. I mean, this should have been, at most I want to see 2, maybe 3 shims. Oh, by the way, the length of the foot. But right now, you took a foot. This is designed for the weight of the machine to be sitting here, as well as a drive end, which is not. It's not designed for the way this is set up. But if I look straight down through there, let's see if we can see it. No, too blurry. But you would be able to see it. But it also doesn't go the whole width. It's just a little bit. So it was silliness. The OEM says, how do we fix it? And I said, you need to put a structure underneath the front end of the motor, and then bolt it and then align it and leave the bolts loose and then tighten them up finally, and then make sure that, because everybody makes an assumption that the machining on a C or D flange is somehow perfect and will have you in perfect alignment. Absolutely not. It is not. Matter of fact, we're supposed to use a dial indicator, and we can allow 2,000ths on that. Now extend that out. You're at some angle out that distance, plus all the other stuff, all the other machining, all add together to be inaccurate. So it's not unusual on those things to see that. So let's take a look. This one is the one we've looked at before a little bit, but I just wanted to show it a little bit one more time, because we went in there and this machine here, and I'll play the video. There's my accelerometer. It's on top of a piece of steel sticking out. What's under here? Nothing. And then I have a rabbit fit. which is not snug and tight, they never are, to an end shield, and then my bearing way down here, right? Then I have another bearing over here. I don't see another accelerometer in a belted application. And by the way, this is not in line with the belts. I mean, you're supposed to have this in line with the belts, in line with the load, so that you can see what's going on. Nope, we don't want to do that. This thing, as I'd mentioned before, was an argument. And we had detected both bad bearings. We detected other conditions with the machine with electrical signature analysis. And an engineer said we were wrong. His vibration data said there's nothing wrong at all. Didn't even show bearing signatures at all. Automated device. I'm going to shape this up here so you can see it. Whoop. Good enough. Okay, and as you may remember, I created a video called "Motor Go Boom" around that one, just to show you. There's nothing under there. That is a bell. That is, it's somewhat close to the core, but it's actually on this side of the core. So I literally have a bell. Dong. So I'm doing the vibration analysis of a bell. So go out to the Liberty Bell, put an accelerometer on it, knock it with a hammer, and tell me you're going to read that. You're going to read the natural frequency. You're not reading the bearing. You're not reading anything of value there. And people keep doing this crap. This was the other part. We started up, and the bearings were so bad that the rotor scraped and pulled it up. So that was the condition. That is, according to their accelerometer, that is a good bearing. That's the opposite drive end. There's nothing wrong with that bearing. It's well beyond failed. The balls are in pretty good shape too, of course. So the amazing fact is that, I had somebody say, well, 99% are not mounted this way. I beg to differ. I would say 99% are being applied this way now. I know in the wind industry, there's a couple of really good vibration folks out there that make it a science. And some of them are the machine learning AI versions of the systems, and they work. Why? They get good data. You get any AI, you get any machine learning system, and you give it bullshit data, you get bullshit results. So, when I put in a system and I give it bullshit data, I'm not going to get good information back, and it's going to tell me something's good that's not. Or it might give me a false positive. Say something's bad, then it's good. So that's the opposite drive end. Let's take a look at the drive end. Close to that accelerometer. So there's a thrust issue here. And you can see some traveling. That is actually a very slight discharge. And there's a reason for that. Electrical discharge I'm going to cover later. I've looked at it for a long, long time. I'm dealing with it a lot. There's a lot of misinformation out there. I've gotten into arguments, especially with those brush people. Every motor needs a brush. And it's like, yeah, but the bearing didn't fail that way. Every bearing fails that way. If there's a VFD anywhere nearby, it's like, that's not how it works. There's a lot more to it. But, if you got a hammer, every screw's a nail. This is just us taking a look at it. This is the outer race that was, measured as in excellent shape. I mean, perfect according to the that vibration analyzer. Yeah, that's perfect. There's not a problem there. There's no discharge going on. That was the setup we made for the proof of the thing. For those who watch the video, this is the pre-work, setting it up, and I'm saying I'm not clear this is gonna make it. And of course, got to throw Bronca in. We went ahead. It was, when we tested it, was part of a bigger thing. All my safety gears in that part. Yeah, and then here's one that I took out at a blower site, and I was taking specific data. Couldn't get down on the bearing, so I took the data up here, but it's primarily so I can take comparison data to the other. They actually had a rod that came up from the back bearing for their vibration program here. So I took data where they were taking their vibration data, which was at least on the end shield, at least on a solid part, although right underneath that, it's curved out, so there's nothing straight over the bearing. So I have to understand when I'm doing this, I'm not taking a direct measurement. Okay, so things to keep in mind. I think that does it for that bit. Yep. Okay, so we covered all that. So let's talk about CIGRE real quick. CIGRE was it's my first year. I went ahead and did the membership too as one of the appointed folks. Wasn't something I needed to. I don't need to be a member, but I decided to join anyways so I could get access to some of the materials. Let me see. I'll give you an example. I don't agree with some of it. And before you go, you don't agree with it. What do you know? It's a whole bunch of people, it's a group of engineers that really cool folks, by the way. Electrical engineers. My area of focus there was on electric machines, wind, stuff like that. We got involved in this study, and in one of these, I wanted to see what was said. I still have to finish reading the document. Won't talk about exactly everything, but there is a one that I will be, in particular, I really want to be involved in. And that one is electrical signature analysis. So it is it not going to show the front page? Come on, show it. Okay, here we go. Technical brochure. This one's on impact of high penetration of inverter-based generation on system inertia of networks. Came out about the way I expected. This reinforced what we did with the IEEE 6800 on ensuring certain power quality stuff as it relates to connection to the system. And that, of course, is also overseen by NERC, FERC, and everybody else. Another discussion for another time. This one that I wanted, A1, rotating electric machines, impact of cycling on large electric motors. Very, very important stuff. I'm going to refer to some of these later. I know a lot of these engineers. Howard Setting, who's now chairing A1 overall. I've known him since the early 1990s. This is going to go through all of the impacts on large machines. Okay, so a good solid study, they normally involve surveys as well. Some don't become, they call them brochures, but a brochure in this case is hundreds of pages. There's some stuff I'm working on related to insulated cables. You'll see a NETA article coming out soon, I assume. I didn't have any good images on testing cables on wind and solar side. In particular, the focus was solar for that one, but this one I got because I want to go through and make sure that when I do when the edit of that article comes back to me and the peer review that that I have some more another reference. Now there is a lot of these. These are the ones that I'm in particular reviewing for my own purposes. DC power systems. This is it. So guidelines for subsynchronous oscillation studies in power electronics dominated power systems. This became pretty important because part of it suggested, again, that that some of the issue has to do with the wind. Okay, that somehow that it's from the wind side of things, and it's not. It's the other way around. So end users, and when I first read this, I was going, "Oh, great! It's going to be another thing." I went, "No, turns out it has to do with end users, you folks, putting this stuff back in the line that's destroying the electrical system." So power electronics and controllers introduce subsynchronous oscillation issues to the grid. Now I want to read this to see how it stacks up. But we were seeing an electrical and torsional issues. So we were seeing on wind turbines the entire thing having to do with what's called a wiring fracture or rotor failures. I published a paper a number of years back after a study done with Timken, H&N Wind, and Shermco and myself, as well as data that came in from Evans, now IPS, and IPS, data that we did. We took a look at it, and we were actually seeing the frequencies that we're expected to see on AC systems in plants in certain applications, such as 16 hertz, 21 hertz, and 51 hertz, that were dominant in the air gap of the machine that was causing fatiguing of the rotor system and failure. Let's see. That one I am very, very interested in reviewing because it further supports the work we're doing on identifying those cases so that we can eliminate them. Another cable, because I'm looking at the cable issues and testing from the solar panels to the inverter, from the inverter to the primary, the transformer, and then the collection cables that are all 34.5 or 69 kV. And this one is, this one has to do with something else that happened a number of years ago that, I still want to go back and give it a little stick it to them from an OEM that gave a customer a brand new machine where they'd cut coils out of the circuit. Pretty nasty. So the next part I pre-recorded, so it'll be a little disjointed from what I'm talking about here. But that will be just showing you this system and quick upload. I actually took it off of a special device I have for taking data off of, plug-in devices. So the data that I'll show is actually from my laptop screen and some other stuff. But remember, current signature only. And it will analyze the the motor and driven equipment. It's not designed for it's not designed for doing transformers. Not designed for doing DC motors yet, or generators. So that system, we're going to introduce it for induction motors. May introduce single-phase motors as part of it, because we spend a lot of time on single-phase motors with ESA because I wanted to know. But in particular, it'll allow for a lot of things. There's no inrush capability to it yet, and a few other things, but there's a reason for that. For the more complex applications or engineering style studies, we still insist on full electrical signature analysis using the empath, which is my go-to. This one here I'm going to use for ground and neutral studies. I'm going to use for testing smaller machines, although it is capable of doing any size machine, just like any current signature. However, there is a weakness between electrical signature and current signature. And electrical signature, of course, has the upper hand. So when we put our literature together, there'll be a discussion of that. We will talk about it more in the podcast. I told you this was in development some months back. I just needed the proper hardware, and we finally found a distributor of the hardware that allowed us to take the next step. So it will do a full analysis and everything else as an affordable tool so more people can be exposed to the ability of using the electric motor itself as the transducer. I don't run into problems with the structure of the bearing. I don't run into problems with the bell issue because I'm reading everything directly with the air gap of the machine being my transducer. And this is part of the reason you've seen a lot of publishing related to the losses across coupling and the belts and so on. It will be an expert system. There's no AI or machine learning needed. It will stick right on your PC or your laptop, actually. It does not need to be does not need the cloud at all. Everything can be done right there locally on your machine. We are looking into phone and other type of tablet based outside of a Windows tablet, but with some security issues that are coming up with those devices, we're sticking to the laptops for right now. But it'll be a jump that we may make for 2025. So again, we are going to make the beta version available. It won't be as pretty as the final version. And when the final version comes out, everybody who has a beta will get it. No surprises, no increased cost, and any data you're taking, because they're going to be sound files, you'll be able to utilize and go back to it. So a lot of cool stuff coming. Again, this is the official announcement because we now have the hardware ability selected, and we have the software closing in on completion for the beta version. February 2025 is the plan for the final version. So that will be available starting in October. We will again have it at our booth at SMRP, booth 313. So here you go. So this is the beta of the MotorDoc MCSA software. This portion is only the upload. So we have a system in which we collect the data like this here. Now the data we're going to collect here is basically off of the system that I'm using to do this recording. But in any case, the basic system allows us to collect some data. The data is going to not be as small as the empath system because it's a different format. Matter of fact, we're going to use a sound format for this. Right now in the beta, the actual waveform won't show, just every 1 second as it refreshes and counts down to the data collection, it will go along this way. Other things are we're not going to allow the specific setting of the amount of time, et cetera, et cetera, et cetera. That way we get in the information necessary to put it through the analytic portion of the software, which will not show in this presentation. In any case, the resolutions for really quick data collection would be 0.1 hertz resolution. That's all the way out to 5 kilohertz and higher, actually, and 0.01, and then 0.001. Now, I don't recommend the 0.001 unless you're looking for very precise data, because that's 1,020 seconds, which is close to 20 minutes of data collection. The other ones, the 0.01, which would be most common even when testing an unloaded motor sitting on a test bench, 0.01 hertz is more than enough for what we want. That capture is 10 cycles. The other one is the peak-to-peak RMS. In the analytic portion, you're going to be able to look at the RMS and a couple other things, because that's all part of analyzing machines. That one will have guided and automated analysis depending on the type of machine. The first one available will be induction motors. This is the 5 kilohertz. This is the 1,000 kilohertz data set. Basically, so you can take a look and see what's going on in the system, especially in a VFD. This one here is out to 140. Now you can zoom in even on this. This is just the simple reporting, and as a matter of fact, on the simple reporting, under each image there's a comment section. Now, one of the things I'm still working on, the team is still working on, is here trying to get the controls immediately under the images. We're doing this programmatically instead of in a visual setup, so it's a little funky there. But this is the other feature we have, where you can click on different spots on each of those. Now, that's not just the spectra, but the rest of it. And again, this is the simple reporting section, just meant to provide information off of a quick data set. The automated analysis for the beta version of the system, which will be out in October and available, will in the final version, which will be free to everybody, will, as soon as you upload the data, it'll analyze. In any case, more on this.